some drinks quality monitoring is another application. Then we're also working with smart irrigation. This is another important field of research, and also application with the moisture measurement industrial gases. So these are the few areas in which we are trying to work and we are trying to contribute something in this field. Okay, so research outcome, you can say we are trying to develop a different type of sensor. Mainly we are working on capacitive sensor. Then we are also working on resistive type sensor, or we are also working on, you can say, an impedance sensor. Then we are also working on surface acoustical sensor. Then in addition to developing sensor, we are also trying to develop different type of electronic circuit. It may be the circuits for capacitive sensor, circuits for resistive sensor, then lossy capacitive sensor, then sometimes we do some signal conditioning also. It may be the non-negative compensation, it may be temperature compensation, it may be hysteresis error compensation or trip compensation. And finally, our main object is to develop some sensor-based electronic test system which can be used for real-time application. So these are the some research activities already. And let us see, as far as the parameter measurement concerned, we try to measure moisture, we are trying to measure humidity, we also measure gas density, gas application. We also use to develop sensor for pressure measurement, sensor for temperature measurement, sensor for thickness measurement, then organic vapor detection for ion application. Then in case of a structural health monitoring, we are working on setting time determination of cement sample or moisture measurement, toxic gas detection, liquid level detection, etc. So these are the different sort of application we are trying to develop sensor. Okay, and then okay, I already have told you the type of sensor we use for measuring those parameters. It may be capacity type or conductive type, or it may be impedance type, or it may be surface acoustical type, or it may be ultrasonic sensor or optical fiber based sensor. So these are the different type of sensor we are trying to work on this. I think you are able to listen to me.
Yes, sir. You are audible, sir. Yes,
okay,
sir.
thank you.
Thank you, sir.
Okay, these research are sponsored by DST. Some of the research is sponsored by Department of Atomic Energy, Mumbai, Board of Research in Nuclear Science. Then some research funded by DRDO, New Delhi. Then another one, CPR Bangalore, this is for GIS application, a Central Power Electro Research Institute, Bangalore. Then sometimes we also get some fund from MHRD. So these are the different funding agencies from where we receive the SPON research project for conducting research in this area that I have already mentioned to you. Now let us come to the topic that I want to discuss today during my presentation. It is basically the condition monitoring using capacitive sensor. So capacitive sensor, you already know that capacitor is basically one of the very basic circuit element in electrical engineering. And if you remember, any circuit you are familiar with, there are basically three passive elements, or it may be capacitor or resistor or inductance, and there should be some voltage source or current source. So this capacitor, and as you know, that capacitor, it may be parallel plate type, it may be coaxial cylindrical type, it may be cylindrical cross capacitor, it may be interdigital parallel plate type, or it may be spherical capacitive sensor, capacitive type, and also the cylindrical sensor. So maybe only in this type of sensor we are trying to work and we are trying to develop the sensor, but we never work on spherical type capacitive sensor. So I will discuss on this in this type of sensor for condition monitoring application. It may either parallel plate or interdigital parallel plate, where some cylindrical cross capacitor. I want to give more emphasis on cylindrical cross capacitor. Parallel plate, we are using that numerous application we find using parallel plate capacitor for numerous application. Okay. Similarly, So interdigitated parallel plate, this is another very widely investigated capacitive structure across the world and for different type of application. So I interdigitated parallel plate or parallel plate structure. These are most widely used capacitive structure for different transaction and sensing application. But you see, even coaxial cylindrical also used for developing different capacitive transduction, but cylindrical cross capacitor, these applications are very new. In fact, we have well started working on cross capacitor sensor very recently. I will show some very excellent result in the cross capacitive sensor. And there is another important sensor that nowadays people are working on, freezing film. Okay, so freezing film capacitive sensor. Now, as far as why I am going for capacitive sensor, so capacitive sensor, it is possible for measurement using contact method or non-contact method. Or it may be you can use for non-invasive sensor or invasive sensor. Or you can say non-destructive sensor or destructive sensor. So in case of a non-destructive sensor or non-contact sensor or non-invasive sensor, your electrodes are not touched with the medium that we are going to sense. So non-invasive sensors are very much durable. Long lifespan is there, and its performance characteristics do not deteriorate very quickly. So it is durable, it maintains its superior performance character over a long period of time, and it is also possible I mean, it nowadays can be used for even for fabrication in a sensor. Freezing field capacitive sensor, this is also another reference of wonderful application. So as you know, the freezing field is normally the back thing for a parallel field capacitor or cylindrical capacitor or coaxial cross capacitor. Fringing field is basically which happens at the edges of the electrode, and this fringe is going to trigger on more capacitor. But this capacitance effect should be minimized by taking proper arrangement. But nowadays, this fringing field can be used to develop some sensor, and that is non-invasive sensor. So it is also that also if I will discuss some part. Even now, let us see some of the application of the capacitive sensor. So you see that it may be directly constant measurement of transform wire or EDB wire. Now it's a film thickness measurement, liquid level measurement, humidity, test master, dispensing and breather. So many applications possible using capacitive sensor for time sensing application. Now let's come to the parallel plate capacitor. Parallel plate is the most simple structure. Okay, so it is having two plates, and in between there is a dielectric layer. Okay, and you know the capacitor and a simple way it can be represented by C is equal to epsilon naught epsilon R A by T. So this expression that normally we see in the books and textbooks, it is only valid when the gap between the electrode is very small with respect to area cross section. So if the gap is small here, so you see in the expression, I mean, this expression already familiar to all of us. But why I have taken it that this expression it guides us. So what are the possible way we can vary the capacitor? So capacitive sensor means we have to vary the capacitor value in presence of transaction media. Suppose you want to measure the pressure, due to pressure capacitance will change. If you want to measure dielectric parameter, then due to dielectric parameter capacity will change. If you want to measure displacement, due to displacement capacitor value change. So if you see this expression, that capacitor value will change either changing epsilon r or by changing the gap between the electrode T or by using the basically the area cross section there of the electrode. So three way, and one application recently explored, that is I mean by grounding by placing a grounded electrode between the two main electrode, high potential, low potential electrode. So this one more new application we have tried to explain to you that this is also going to have very linear response of the capacity. sensor. Okay. Now this is, and let us see. Now we are going to make a capacitive structure. As already I have told you that at the edges of the electrode there is a fringing field. So in this case, you see these are at the edges there are basically the fringing field. Okay, and you know that in order to basically low potential electrode and a high potential electrode. These are basically two main electrodes. Okay, and the capacitance, it is assumed that the electric field between low potential electrode and high potential electrode is parallel. But at the edges, this electric field is not parallel. So this is also going to result on capacitance, that is called fringing field capacitance. So, in order to minimize the fringing field effect or that capacitance that arises due to fringing field, you have to use a guide electrode. That is basically the whole concept that is there. But let us here I have shown you that how we will place the guard electrode, or you can say guard ring. So, you see that the guard electrode, it can be placed either around the high potential electrode or around the low potential electrode, or both high potential, low potential electrode. Okay, but placing the guard ring around the hyperelectric sufficient, you can get a stable capacitance value. But when you are going to place the guard electrode, you have to decide that what will be the diameter of the guard electrode, what will be the gap between the guard ring and the high potential electrode, and what will be the gap between low potential and high potential electrode. So these three equations I have shown here, that this is basically the capacitance epsilon not epsilon r a by d. This is the guard effect. This is should be less than e to the minus pi c by d. Okay, so this effect when you are going to design or fabricate the parametric capacitor, you have to maintain this condition. That is this part. This is basically this sequence. Let us say this is a diameter. This diameter should be so that the c by d and minus pi is equal. This part is basically this guard part should be equal, and this is given by n eta gap less than e to the minus pi c by delta. But this is basically the gap. So in roughly you can say that this diameter should be at least 5 to 10 times more than the gap between the guarding and high potential electrode. So if I am interested to design any capacitor, parallel capacitor of good quality, maybe it can use a reference capacitor, then you have to maintain this geometrical condition when you are going to fabricate this structure in any machine lab or something, some structure. So that gap should be very small with respect to this diameter. So, okay. Now, see here that when you are going to design a high quality capacitor, suppose you know the capacitor can be used as a standard also in case of the instrumentation within application, or as a reference capacitor. Okay, then what are the factors that you have to keep in your mind? One factor is that capacitor value should be highly stable, low effective environmental factor, free from dirt and electrode culture. It means your electrode should not get oxidized. There should be any dirt accumulation. There should be no drip in material, and extreme care should be taken of the parasitic arc capacitance, because you see that wherever the two terminal of the capacitor, if there is a potential difference is there, then that it is a forming a parasitic arc capacitor. So that capacitor is going to affect the actual capacitor value between the two electrodes. So you have to take precaution, take some measure to minimize the parasitic arc capacitance effect. And also that sometimes bringing your hand, human hand is going to cause some interference. It change the capacitor value. So you have to avoid this thing. What is the best one? The parasitic arc capacitance, it also basically it is a fluctuating parameter, which is changed. So if you want to avoid this thing, you have to use a shielded cable you have to provide the metal seal, and also the length of the capacitor lead should be as small as possible. So these are the precautions that you have to take in if you want a capacitor of high quality and particularly for low frequency range. This is one design that I have shown here, that in fact we have fabricated. This is quite a good quality capacitor. So how it is made? So in this case we use a brass as electrode, and we use the insulation between the two plate, low and high potential, is a Teflon. Why we have said to take Teflon? Because Teflon is a very highly hydrophobic material. And you know that moisture is basically a troublesome parameter. And moisture is present everywhere. And moisture can affect the dielectric parameter value. So you have to select those material which is not having any moisture effect. And that is basically, this is Teflon or PTFE. This is one of the excellent material which is extremely hydrophobic. So we can use Teflon material as a dielectric between the two electrodes if you want to fabricate a capacitive standard of high quality for low value. Then I have shown to you that basically it is having, we have selected the brass electrode 62 mm diameter, low high potential electrode is 45 mm diameter, and then this is basically a guard rail. This is the guard rail, and there is a small guard. At least it takes 3:1, something like this one. At least 3 times more diameter than this gap. And this capacitor value is basically 30. If you select this dimension, then its capacitor value is 30. So, and one more thing, that after making this capacitor, whole structure is placed within a metal sheet. The metal sheet is made of aluminum tape, and so that later this metal sheet can be grounded. Then in parasitic arc capacitor, it has a fixed value, but it is not changing. Then by using some circuit, we have to minimize the parasitic arc effect. So as far as electrode is concerned, we can use aluminum, we can use copper, we can use brass, gold, platinum. So you know that according to the cost, that if you're taking gold or platinum is very inert material. Gold is a very inert material. We can use gold and platinum as electrode, but it is basically costly material. So we have to make a compromise that whether we have if your design requires very high precision, high-end application, then definitely we have to go for gold or platinum, because in that case cost also the border. But if you want to have a low cost device, low cost application, then you can use brass. Aluminum is the worst material. It is oxidized very easily. We are all familiar with aluminum dishes that we use in a household application. If we want to today, you have to wash it clean properly. Otherwise, it gets easily oxidized. So aluminum can be used, but it is oxidized very easily. Copper is also get oxidized very easily. So brass is a basically alloy material. It is quite good quality material which can be used for electrode making. So we normally use brass for making the capacitor. Then I already have told you the insulation. It can be your Teflon, or you can go for PTFE or acrylic. Can also be acrylic. Basically, your now I think familiar with acrylic sheet. It is used for our daily use. And also nowadays another very important polymer material getting very popular for sensing application for biomedical and different application. This is a polymer material, but it is compatible material. At the same time, it is hydrophobic also. So it is also we can use for fabricating capacitive sensor. Now this is that the dimension that depends on your the value that you want to design. So this is one capacitor that we made in our lab. This is called 2 picofarad capacitor. So you see, this is basically a metal seal, aluminum metal seal, and the electrodes are placed inside this aluminum metal case. Okay, and we have taken basically coaxial sealed cable for making connection to the measurement device. So this is one 2 picofarad capacity value. It is called a straddle and or more structure that we made. That one structure is basically this capacitive structure we made for measuring the quality of individual wire. So individual wire, you see that sometimes people for earning more money, they mix some low quality wire to the good quality wire. So it is very difficult to identify how to whether it is a mix up or not. So basically, this is one work that we do. So how we have done it? We have the structure having two parallel identical capacitor. So this is one capacitor, this is one electrode, this is another electrode, and this is another electrode. So between these two electrodes, this is one capacitor, this electrode and this electrode, where there is a capacitor, one capacity is formed. Similar, this electrode and this electrode, another capacity is formed. So these capacitor both are identical. Okay, then these two, they are basically the black one is the insulation, and this one is basically the brass. So electrode is brass, your metal shield is brass, insulation is basically Teflon, okay, and this is on end where you can put the wire, and this is basically your air capacitance. So here we are trying to measure the dielectric constant of the liquid sample. So dielectric constant is basically the ratio of capacitor to individual wire and to the capacitor of air capacitor. So this ratio for asymmetric operation is going to nullify different effect because both is having identical effect is there. So that is it is quite reasonably precise method for measuring the quality of oil. Even you can use this structure for measuring the moisture quality in transformer wire. But we have used this structure for making the direct constant individual wire. Okay, so let us see. This is the structure that we fabricated in the lab. I will show you information. This structure may be around 10 to 15 years old, but still its capacitor value is stable. Okay, so this is basically brass metal sheet. This is a brass electrode, and this is the Teflon insulation. And it is having two identical capacitors. One on this side, another on the opposite side. This is the hole through which you can apply the wire. Or you can, this should be the free space capacitor. This should be the coupled with the wire. So this is on one structure is similar, and this is the razor that we recently have taken. We have taken two types of wire we have used here. This sunflower wire and this is mustard wire. You see, for sunflower wire, the capacitor value is 3.0936, and for double filtered mustard wire, it is basically 2.936 value. You see, this is one more thing I want to tell you that this wire value constant do not change much. So that is why it requires a lower precise structure for measuring capacitor value. This side is basically ultimately this capacitive sensor is interface with some electronic circuit, and that is basically the oscillator based circuit. In the time permit, I will discuss about the oscillator circuit also later on. Okay, so that gives the frequency output. So this is interfacing output frequency change due to the so it means here we have tried to repeat the experiment so many times. 1, 2, at least 8 times we repeat the experiment, and its average value is more or less around 3.0936, and this is the average value 2.969, something like this one. Okay. So this lower is the master wire, upper one is the sunflower wire. This is one more structure to use for thickness measurement. So our main purpose is to measure the thickness of sensing film. So we are going to fabricate some sensor for maybe 100 micrometer thickness or 200 micrometer or 300 micrometer thickness. We normally use some conventional laboratory analytic instrument, basically electromagnetic techniques is used. So optical techniques based instruments are very costly. So what my aim is it possible to develop some capacity type technique in the lab so that we can measure the thickness of the sensing film also. So here this is the structure that we use. Here also we are having two capacitors there, two identical capacitors. One is with the film with thickness to be measured, and another one with the film. So this is the air capacitor, this is the film capacitor. And purpose of this design, this is the actual photo of the setup that we have developed. It is we can measure the thickness as well as the film uniformity. Because film, we are going to make a sensing film for sensing application. The film uniformity also vary. Say for example, you are making the film using deep coating technique, or suppose spray coating technique, or suppose some drop coating technique. So there is a possibility of non-uniformity film. So you have to measure the film thickness also. So how to measure it? So this is basically the provision here. We can move this electron laterally. Okay, so here we can moving the electron laterally. We can check whether at different areas of the sheet or film we are having identical capacitance value or not. If there is a variation in there, it means your film thickness is different. So here technique is very simple. That is here C, as I have told you, the C can be varied either varying the thickness or varying the area of cross section or varying the epsilon R. I have given an example of how epsilon R can be used to develop the capacitive sensor for measuring the quality of visible light. Similarly, by measuring the film thickness, by varying the gap, so you are also going to measure the T value. Okay, so you need to see. So this is basically our experimental setup for measurement purpose. What is that? This is the where we are taking the reading initially on L meter. So this is connected, both is connected to this one to take the measurement. For and we have taken different type of sheet. We have taken Teflon, we have taken basically polymer sheet, which series of film, different type of sensing film. Then we try to calibrate this sensor for future measurement applications. So this is the reading. I have shown to you that this reading is basically for measuring capacitance value for Teflon sheet. So we have taken Teflon of 1 mm, 1.5 mm, or 2 mm, 2.5 mm, 3 mm, and 3.5 mm. And this is the capacitance value. So as you know, the capacitor value in case of a gap between electrons is inversely proportional, and that is why as we are going to lower the thickness, then we are having more capacitor value. It is inversely proportional. And one more thing, if you are having a very low thickness, then capacitors losses thickness almost having almost inversely linear response to the getting. This reading has been taken at two frequencies, one at 1 kilohertz and one at 10 kilohertz. But you see that both frequencies, the capacitor value is almost identical. But at least this structure, this device, we can measure in the field thickness very effectively. This is the table that will measure the diameter field thickness of different material: Teflon, alumina, glass, and hard paper. Okay, so hard paper is there. So Teflon, I have taken 1 mm, capacity measured at 1 kilohertz, 10 kilohertz, and 100 kilohertz. Then alumina is thickness is only 0.372. You can say 370 micrometer thickness is there. This is the value, is capacity value. As you are going to lower the thickness value, more capacity value is there. Then glass substrate 0.6 mm. So this is 7.850. Okay, and hard paper, that A4 size paper sheet, this is around 0.247 240 micrometer thickness is there. So accordingly, capacitor value is more. So if we let us see, if you want to compare the 1 kilo frequency, lower thickness, more capacitor, this one. So it may just it requires a little bit, means it can interface to PC, then you are having capacitor value, then you do little do calculation, because you should know what is the material, because you are calculating P thickness based on epsilon R. So epsilon R of the material should be known to us. So if you do this value, then we can find what will be the capacitor value. Okay, so if you have any question, you can ask to me for the time being, or is it okay? You are able to, my voice is clear. You are able to follow me.
Yes, sir.
Oh, so if you have any problem, just you can also inform me also.
Okay. Please go ahead.
So I'm going on well, isn't it?
Yes, sir. Yes, sir.
Okay, thank you very much.
Thank you, sir.
So next is that here we have developed on prototype digital hydrometer for ppm moisture measurement in electrical apparatus. So I think you're all familiar for moisture measurement, and moisture is having very wide dynamic range. In our real-time application, we need to measure RH level from 99% or 98% RH to trace moisture in the range of parts per billion to parts per trillion application. So some critical application where I have to measure moisture in ppm level, that is on transformer wire. In transformer, we have to measure moisture even less than 10 ppm. So in the commercial viewpoint meter that is meant for moisture measurement, it may even find the range from 0 to 100 ppm or 0 to 1000 ppm. But it should also have a sensitive range even less than 25 ppm. So here we develop on and some application of the sensor ppm moisture sensor is basically the moisture measurement in SFC gas that is used in switch gear and protection system. Some other application of this is basically your it may be the petroleum industry or plutonium globe blocks. In nuclear power plant, the plutonium pellet, it is moisture level is going to affect the fuel value of the plutonium radioactive material for electricity generation. So that is also some critical application for ppm moisture sensor in liquid. So here, this is what is that. So what is the idea? We're using parallel capacitor. Your sensing film is aluminum oxide, porous aluminum oxide or porous titanium canals, but we have used porous aluminum oxide. And why you have been porous? It is a very stable material thermally and chemically. It is inert material, and also it doesn't have any temperature error. So that is why we have selected the aluminum, and it is a porous. So it is having wide ample spaces available for condensation of vapor molecule even a trace level or ppm level. Imagine our target is to measure moisture in the range of 0 to 100 ppm, where moisture molecule is out of 10 to the 6 part, only 10 part, 20 part, 30 part or 50 part moisture molecule is present. So very small moisture concentration is there. So in that case, we need to have ample space for moisture condensation. So even if small space is available, then your capacity value should change. And for that, porous material is very suitable one. And its pore morphology is also very important. That is size should be small, because as you are going to reduce the size range of the moisture measurement, your size of the molecule is going to be smaller. So we have a smaller pore. So here we use the solvent method for fabricating the nanostructure. Then we use the deep coating for depositing the film, and it is basically the electronic circuit is developed for the output. So this is the structure. This is the lower one where it is the structure. So what is that? We are having a substrate. It is the base material. It is a platform on which there is an electrode. That electrode may be, in this case, gold electrode is used because it is a special sensor. This sensor in the commercial market is very costly. Even if you are going to purchase this type of structure in commercial market, it costs around 75,000 rupees. It is a special application, special requirement. It is costly. So initially we try to use gold electrode, and then over this there is a sensing film, aluminum oxide. Then over this there is another gold electrode. So there is a sensing film between the two electrodes. So it is a parallel plate structure. Here you see that in this case we do not provide any guard electrode. Okay, why we do not provide? Because here you see the thickness is hardly 10 micrometer, and your electrode size is maybe 10 mm by 10 mm. So electrode area is so large and gap is so small, then its film at the edges will be have a negligible effect. But in case of bulk material, we have to take precaution of this situation. So we have used this structure, but this is another structure for interdigital electrode structure for mastering, but it is useful only for low higher RS value measurement application. So how we are fabricated is that we are having a original part we have done because I am explaining here. But initially we are having a substrate is there. The substrate has taken a sapphire material. It is basically the alpha alumina substrate taken. Alpha alumina, which is fabricated at very high temperature, at 1200, even more than that temperature, it is made. So this is the material I have used, base material. Alpha is there. Over this we deposited a gold electrode by simple nano screen printing technique. Okay, then gold electrode is heated at 900 degrees centigrade temperature for 1 hour. Then over the gold electrode we deposited alumina film. That alumina film is prepared from Solzel method. It's electrochemical analysis. It is a chemical route where we have the elements of hydroxide and water by hydrolysis process and peptidization. That salt solution prepared, and then from that salt solution we do a film on the metal electrode, and then that metal electrode and metal oxide film is heated at 500 or 450 degrees centigrade temperature for 1 hour or 3 hours. Then once aluminum oxide is fabricated, then over the top of the electrode we deposited another electrode. Okay, you may ask, so if we deposit another electrode, how master molecule go? The top electrode is made by screen print, and normal screen is based on some, you can say, silk material or some mesh is there. So the mesh is having basically very wide pore, and this lower aluminum oxide is having very small pore. So master molecule can easily pass through the top gold electrode and can deposit on the metal oxide sensing film. So that is the it can easily pass, and so this is the step that I have followed here for fabricating. This is the structure of Lattice. You see that this is basically efficient image of aluminum oxide. See, those black dots is basically the pores. And what is the dimension? You see, this scale is 200 nanometer. It may hardly less than 10 nanometers pores are there. So as I told you, we are having a small moisture, so low moisture dimension, diameter of the molecule is small. So we need the pores of smaller size so that moisture molecule can condense once it is getting in the pores, and this is also going to change the directive constant. So these are the sensors that we have fabricated in the lab of different capacitance value. This is the small one. You see only this small black dot, it is hardly 2 mm by 2 mm, but it can easily sense RH value significantly, but not able to sense the ppm moisture. This is the most sensitive for ppm moisture because it is having a significant area 0 to 100 ppm. So here also we fabricated different sensing range, and this is the experimental setup for determining the response characteristic. So we are having one deeper meter, commercial deeper meter. We use as a reference meter to measure the moisture content in the nitrogen gas, and then we record the capacitance value of this one. So this is how we do the experiment. So this is the chamber where we place the sensor. This sensor connected to the impedance analyzer to determine the response characteristic, CPD or J theta, something like at different frequencies. And we are allowing the moisture molecule of different concentration to pass through the sensor. And the same nitrogen gas with certain moisture is allowed to pass through the standard meter. Okay, and we are able to get down for that what is the moisture level in the gas and corresponding capacitance value. This is the reading we are showing. So you see that moisture molecule vary from 0 to 25 ppm. Okay, and you see the capacitance value changes from around, you can say 1000 around 1 nanofarad to, you can say 1.06, around 60 to 17 picofarad capacitance changes there at different frequencies, and almost all the 3 frequency capacitance values identical. And this is the response parameter. I have not gone all the detail. What is the data set? This is the range, this is the capacitance value, this is the sensitivity, response time, recovery time, nonlinearity. So all these parameters that you have to measure, because in the commercial device also they are having some data set. Okay, so this is basically the panel plate structure for measuring moisture in people level. Later on I will show the reading of dew point meter as I told you. hydrometer reading. I'll say in the going on this about the circuit. Okay. Now this is basically another application of capacitive sensor for moisture measurement in transformer wire. So in this application, as I have told you, less than 100 ppm should be measured, and transformer environment is chemically harsh and chemically rare. So again, this is a structure that we have used. It is a parametric structure, the same structure that I have shown in the previous slide, but here instead of using the gold electrode, we have used silver electrode. And there is a one substance which is available in the market that is called a pure substrate. So it is a fluorine doped tin oxide. Fluorine doped tin oxide is deposited on black substance. So already there is one electrode in this substance, and we deposited metal oxide film by again solder method, and we deposited on silver electrode. So this sensor is much more lower cost, inexpensive than the previous one, because it was made using the gold electrode. We have the gold test, but here we are using the silver test. So it is much more still expensive. And another thing that the response is also very significant and quite sensitive. So this is the response in case of a nitrogen gas for 0 to 100 ppm. This is the capacitive value. Quite high sensitive capacitive value is often here. This is the repeatability. For step change in moisture from you can say 5.8 to 80 ppm, something like this one. So almost it is same pp of take. Okay. Then we perform experiment using transfer wire. This is the setup that we have developed in the lab. Okay. So this is basically we are having a how we are trying to measure the capital moisture value. We are having a oil with different moisture level. Then we are heating the oil. Then moisture molecule comes out from the oil, and that moisture is taken out by the nitrogen, dry nitrogen gas, and then taken to the sensor chamber. So this is basically oil based on heating mantle, and then this is the sensor chamber. So this is nitrogen gas. The nitrogen gas carries through the moisture generated from the transfer wire, is taken through this some pipe, and it is exposed to the sensor, and sensor is connected to the impedance analyzer. Impedance analyzer is connected to the PC for data acquisition. And this is the reading at different temperatures. You see, we are having a three types of wire. One is basically phase wire. One is basically aged wire. This is basically aged wire means those wires which are rejected because of the impurity and some moisture level. And also, so basically, and add different aged of phase wire, and then a 0.5% water content wire. So three different wire we have taken, and you will find that in case of phase wire, reading is horizontal. Now in case of both aged oil and 0.5% oil, capacity value increases with increasing temperature. Then from this, we can obtain a response curve from moisture versus capacity value. Because we know, because from here we have a calibration curve that if you know the capacity value, we can find what is the moisture level. Okay, so here we are getting the capacity value. So from capacity value, we can calculate what is the moisture level. So this is the calibration curve, and this is the agent reading. Agent oil, phase oil, moisture. So as we are varying the temperature of the oil, what is the moisture level in that temperature, we are able to get it. So this is how we are trying to measure moisture in the oil in an indirect way, not by placing a sensor in the transfer directly. But what we are trying to first extract the moisture from the oil by heating it, then that moisture is allowed to pass through some through nitrogen gas and export to the sensor, and we are able to get the reading. Then moisture measurement asepsis gas for GIS application. So this is another application. So now why it is required? That also I am telling you that the arcing, as you know, that in case of GIS, when there is asepsis gas is there, which is for quenching the arc. But whatever during arcing, whatever temperature causes dissociation of asepsis molecule into sulfur and fluorine. But which latter is recombined to become asepsis gas. But in presence of moisture, the recombination process is not properly taken place. So what is the problem? In a asepsis gas, GIS application, when you are having different contact isolated surface. So if there is arcing is there, due to this arcing, the SF gas is dissociated into two components. One is S and another is solid. But when temperature falls, then it is recombined to become SF gas again. But what happens in presence of moisture in SF gas, the recombination does not take place. So it is forming a hydrogen fluoride gas. So hydrogen fluoride is a very toxic gas, and it basically corrodes basically the metal parts, or you can say the other parts in the GIS system. So this is basically the part we have to measure the moisture level in the SF gas. A particular level is allowed. It is same value is, you can say, less than 100 people, but it is desired from 0 to 1000 people again. Okay, so this is one more application that we have explored here. Even we have used the same sensor, that is Goniometer capacitor using FTO substrate. This is our sort of experimental setup. This is commercial saw dew point meter. This is our sensor chamber, which is having some pressure measurement, temperature measurement, and also the moisture able to export. And this is the reading. As we are going to, this is in presence of nitrogen gas, or you can say this is in presence of SF gas. Okay, at different, and this is the reading at different frequency. So at different frequency, the capacity value decreases particularly at higher frequency. It is also having certain reason for this type of response. This response is basically the repeatable. This is for, you can say, response time and recovery time. This is another, because normally for any sensor, when you are going to study, two types of response characteristics study. One is called dynamic response characteristic, and it's called static response characteristic. The static response characteristic means we have to find sensitivity, we have to find nonlinearity, we have to find hysteresis, we have to find basically deadband, range. So all these parameters are in the category of static characteristic. That in case of static characteristic, your input is not changing, constant, or it is slowly, very slowly varying. But in case of a dynamic response characteristic, where its input is state changes there, maybe it is state input or some other type of input is there. So we try to determine both static response as well as dynamic response. So it is also shown here that it basically sees how the readings are very, you can say, moisture level 244 per 6 ppm. It is stable. Okay, as we're going to increase the moisture level, capacity value increases. 505 capacity value increases, then 59 capacity value increases. And this is basically doing experiment in presence of SF gas and also N2 gas. So in the both the cases, you can say more or less sensitivity is same, but response time is different. Why? Because SF gas is a heavier gas, nitrogen gas is lighter gas. As you know, the SF gas is heavier gas, it doesn't allow to know. So that is why response time also is going to increase in this case. And this is the comparison of our sensor, source sensor, commercial sensor, G dynamic based commercial sensor, and basically Zentur Corporation. So we try to compare the performance of our sensor with respect to 3 commercial brands. Okay, but in our case, we do experiment in SF gas, but in all the other cases, they do in nitrogen gas. Nitrogen gas is lighter. So you can say the response is quite comparable. Even many things are better, but only you see the response time is slower. Why? Again, same reason. Because we have done the experiment in presence of SF gas, so that is why the response time is more with respect to nitrogen gas. Okay. Now, this is one more application. Here, this is coaxial cylindrical capacitor for pressure measurement. Okay, so it is now this one more application here. This is for pressure measurement that we are using coaxial cylindrical structure. So what is that in coaxial cylindrical? You see, we are having a 2 cylinder. Okay, and there is a gap between the 2 cylinders is there. Okay, so in this case, what we are trying to do, we are moving a metal plate between the 2 cylinders. coaxial cylinder. This is the blue one. It is a high potential cylinder, and the yellow one. This is the low potential cylinder. So one capacitor will form between this lower and higher, and the red one, it is a metal plate which is moved along due to the application of pressure, and the black one is basically the metal shield. And there is one small gap on the high potential. This is called for guard ring. So upper one is, this is basically guard ring. This is the guard gap, and this is the high potential high potential cylinder. This is the outer cylinder, and this is basically the metal shield. And here, this is basically this red cylinder plate is maintained at ground potential. So we are basically seeing this ground potential, this terminal is connected to the metal shield. So this metal shield and this shield is at the same potential, and which is at the ground terminal. So what happens, as we are going to move the plate from lower to upper, then it is basically electric field passes from high potential to low potential. So what happens? The field is now bypassed from high to ground terminal. Does not allow to go to the yellow terminal. So that is the capacity value change. Here, this capacity is from a three-terminal structure. This is CAB actual capacitor, C1 with respect to ground, C2 here is shown here with respect to ground, with respect to ground. Just a minute, sir. Answer.
Yes, sir. Yes, sir. Okay, sir. No issue.
ভালো আছি, তুমি এত ফায়ার লেকচার চলতে আছে, ইউনাইটেড শিলচার হ্যাঁ এফডি ফোন আমি পড়া করছি, ঠিক আছে? আচ্ছা ঠিক আছে, আমি কখনই কথা বলছি। Sorry for interruption.
No issue, sir. Please, please.
So, so here we are trying to explain the coaxial cylindrical structure with grounded shield. Normally, we do not find this type of idea for sensing application. So, we are trying to place a metal shield which is grounded between the two electrodes, and it is moved according to the applied pressure. And this is forming a three-terminal capacitor. So, this CAB is our bizarre capacitor, C1, C2 are unbizarre capacitor. So, this is the ANSYS model. Okay, so we are having, this is the red one, the inner one. So there is basically insulation, then there is a gap, then again insulation, then there is basically outer cylinder, and this is basically a outer metal shield. And this is the red one. Okay, this yellow one is the high potential. Okay, this yellow high potential. Red one is the metal plate that is moving. And this capacitor, this is the expression. CF is called 2 pi epsilon naught L minus H 1 by E epsilon L R is by R1 plus 1 by R. This all is angular constant. According to the diamond, because epsilon is constant. These diamonds are dimensional parameter. So C varies due to variation of H. L is total height of the high potential electrode. H is the movement of the electrode of the metal shield due to the application of pressure. And you see, this having on linear relation. See, directly proportional, but it is inversely. That is, it is decreasing, but it is having linear relation. That is the important characteristic. This is the experimental setup. Whole setup that were made in the lab. Okay, so all the it is made, and we are having capacitor maybe using the LCR meter. Okay, this is the metal plate that move. And here we just how it is made the ground potential. Where is a mercury? Because mercury is basically heavy metal, and this metal shield it floats on the mercury, and this is mercury is basically metal container. So just you ground this terminal. So all these things are grounded. And when we apply here, we apply the pressure, and that pressure is measured using this pressure gauge. And this pressure gauge is basically the pressure gauge which is used for sphygmometer. That is normally clinically it is used. Okay. And this is the range. This is pressure is varied from 20 to 180 mmHg. This is the range of human blood pressure. Normally, our meters are calibrated. And you see, this is the experimental how linear it is. So, relation is 0.272 to 40 is the L, and H is changing according to the movement of this. These are the parameters. This is the range, this is the capacity value, this is rise time, recovery time, non-unity 0.3%, distance is 1.6%. Even the capacity value precision can further improve by taking a little bit precaution of the terminals particularly. Now I came to the first parallel plate coaxial capacitor I have discussed for sensing application. Now, capacitor values, what are the disadvantages? The capacitor value depends on multiple geometrical parameters. And you have seen it, depends on A and gap between A. And capacitor value changes due to misalignment. Suppose the electrode is not exactly parallel, so there is a capacitor value change. And the sensor requires calibration. So, what is the reason? The cross capacitor, it is having a single dimensional accuracy. It means the capacitor value depends only on length measurement. So, if we can measure the length, we can measure what is the capacitor value. Okay. It uses as a primary standard in national laboratory. It is so precise, it is used as a primary standard. But its capacitor value is good. That is the thing. Okay, so here we are trying to use this cross capacity structure for different application. What is the application? Where this is basically that we want to fabricate cross capacitor using flexible double-sided copper-cladded polymer. This is basically double-sided copper-cladded polymer. This is basically a PCB substrate. But this substrate is having metal film on both sides. This type of PCB is used for in a display device, in a mobile phone or in a laptop. We use this type of PCB substrate. It is flexible. You can mold. You can give a different shape. It is flexible. And what process is followed? Inkjet printing and chemical. And very inexpensively we have fabricated that device. Okay. So, what is the cross capacitor? Let us see how it is done. Cross capacitor, it is having take a hollow cylinder, metal cylinder, and this metal cylinder coaxial hollow symmetric cylinder and divide this cylinder into 4 equal parts. So, you take a hollow cylinder of everyday cross section, divided into 4 equal parts. And each part is separated by a small insulating gap. These are the insulating small gap. You can place some Tesla to separate all the 4 electrons. Then the capacitance between 2 opposite electrons. Let us say this is A is 1 electrode, B is another electrode, C is another electrode, D is another electrode. So the capacitance between A and C, this is called cross capacitor, CAC. Then capacitance between B and D, between 2 opposite electrodes, it is another capacitance CBD. Okay, so these are basically called the capacitance between 2 opposite electrodes. It's called the cross capacitor. So we are having 2 cross capacitors, one between A and C, another between B and D, and this is the schematic. So this is one electrode, this is another electrode, this is another electrode, this is another. All the 4 electrodes separated by a small gap. So capacitance between here and here, cross capacitor. Between this and this is another cross capacitor. I think it is audible, and we need some 1 or 2 minutes rest. Or should I continue? Dr. Deepan?
Yes, sir.
Okay.
Yes,
So continue, 1 or 2 minutes break you want.
yes, sir. Yes, sir. Okay, no issue.
Because see, ultimately our mind is also getting saturated, no?
Yes, sir. You can, sir. You can.
No, it's okay. Fine.
Okay.
So just a minute. So how long was yes, sir. Okay. How long I have to continue, Dr. BP?
Sir,
How
Please.
long? Can I take 25 minutes or more?
Yes, sir. Yes, sir. Please continue, sir.
Okay. Okay, then once again I am coming back to your PPT. Okay, now let us see the theory. Okay, so this cross capacitor, it is based on Thomson and Lamport theory. And according to the Thomson-Lamport theory, the cross capacitor value per unit length of the electron in background is given by e to the power minus CAC pi by epsilon naught plus e to the power minus CBD pi by epsilon naught, and this is equal to 1. If the two cross capacitor identical, suppose CAC is equal to CBD, this is possible because we are having a symmetrical coaxial cylinder divided into 4 equal parts and there is a gap. So we can make two capacitor identical. In that case, the capacity value for length L and with directly constant epsilon R. So this is epsilon naught epsilon R is equal to epsilon naught epsilon R ln2 by pi into L. So let us see the cross capacitor value. If length is constant, then it depends only epsilon R, isn't it? So this capacitor value gives, you can say, single dimension accuracy. If the L is known to us precisely measure, then we can get the value, capacity value is related with the epsilon R directly. It is just like the multiply factor. We can display directly the capacity value. So application of a cross capacitor. So what is the application? The micro droplet detection using cross capacitor cells is basically the automated dispensing system. So what is the idea? Purpose is identification and quantification of micro droplets. Okay. So what are the features of the sensor? It is non-invasive, simply structured, easy to fabricate, cost-effective, fast, accurate, highly repeatable, and there is no drift. What may be the application? We can go for automatic dispensing system, detection of chemical reagent, control drug delivery, in dispensing for printing technology, industrial process dispensing adhesive, coolant, lubricant, identification of different organic vapors, droplet coating of chill film, food technology, and many more. So how the sensor works? So we are having 4 cross electrodes in the cross structure, and if there is a droplet is there in between the 4 electrodes, and if these electrodes are excited, then let us say B and D are grounded, and A and C is excited by V AC voltage, and if there is a drop, and this drop material, so it is having some directly constant. Then in that case, the cross capacitor value between A and C will change. So CS is a cross capacitor, and one capacitor formed between electrode this and this, one between this, so it is basically space AB and CD. So it is forming a 3-terminal capacitor. So here also our desired capacitor is CAC, and CAB and this is AB and CD. It is a grounded parasitic capacitor. This can be nullified by agents of circuit. So free flowing droplet passes through the dielectric field, relative permeability changes, so capacitor value changes. So this is the simulation. So without droplet, this will how the electric field changes in presence of droplet. See, electric field in presence of droplet having the tendency to pass through the droplet. So this is going to change the capacitor's value. Here there is a less chance, but here there is a more tendency to pass through. So it is basically we are trying to play with electric field and we are trying to detect the droplet. So this is the structure that is fabricated. So we are having one. This is basically a hollow Teflon tube, and over there is a 4 electrodes are there, cosplay A, B, C, D, very small gap, and there is again an insulation, and outer there is a metal seal. Okay, so this is basically it. And how it is made? Using copper cladded polymer substrate. As I told you, the polymer is having metal film on both sides. So on one side we deposited 4 electrodes, and on the other side there is a metal film, and the two metal layers separated by polymer substrate, this insulation. So we can easily make this structure using polymer substrate. This is the structure using flexible substrate. This is metal shield. This is basically the polymer substrate, and in between, inside there is a 4 electrode, and this is the Teflon pin. This is the static flexible substrate. This is the bulk material. And when you are going to place the bulk material Teflon tube, then your relation is going to change. And how much is going to change? This is given detail in our paper. You can use this expression. The capacitance value change by factor of 1.008. So only 0.8% capacity value changes because of the placing the directive layer within the electrode. Okay. Now this is the interfacing of the sensor. This is the three electrode pi structure of the capacitor. We use an evaluation board. It is available commercially. This is called capacitor digital converter. This board is having a resolution of 1 femtofarad. Okay, and it can measure even 1 femtofarad change in capacitance value. This is the experimental setup. So this is basically the board. ADC 7150 board, and this is our sensor structure, and this is the dispensing system, droplet dispensing system just placed on this board, and it is interface to PC. PC is the laptop recording the data, and see this is how beautiful the reading is. So first experiment is conducted with water droplet of different volume. So this is the reading, the capacitance peak when there is a water droplet volume 9.3 microliter. This is the peak for 8 microliter. This is the peak for 6.7 microliter. This is the peak for 5 microliter, and this is the peak for 3 microliter. See, as we are going to decrease the volume, your capacitance peak is also going to decrease. So it is basically sensing the quantity, quantification of the droplet. Okay, so you see the moment droplet passes through the tube, inside the tube, momentarily capacity value rises, and then it is good because why it is happening? The droplet is momentarily going inside the sensor and pass out. So the moment the droplet is within the sensor, there is a rise in capacity value. Once droplet goes out, the capacity value also dies out, and that is why this is the situation. So this is basically the dealer black, which is indicating the best capacity value. This is the change in capacity value due to the droplet. So this is for, so you see it is beautifully detecting the droplet volume by giving a distinctive peak of the cross capacitive sensor. How it is, how it changes so beautiful. It is distinctive, isn't it? Then we also do experiment of different type of droplet. We have taken water droplet, ethanol droplet, and acetone also. You see, for all the three, we are having a different peak. But for the same droplet, we are having the same peak. 2 water droplet, identical peak. 2 ethanol droplet, identical peak. 2 acetone, identical peak. But since the direct ethanol, acetone are basically almost close, only small difference is there. So there is a capacity value change is there, but it is small because of this small change directly comes from the acetone with respect to ethanol. So this is basically identification of liquid droplet. Different droplet it is able to detect. Then we also find the conductivity of the water droplet. So what we have done, we added different concentration of salt. Then we vary the conductivity, and we just keep the droplet volume same. So this is basically the peak when there is no salt. When there is a 1 more salt is there, this is 2 more salt, 3 more salt, 4 more salt. So according to the salt concentration, the droplet volume is also going to, or peak is also going to change. This is the repeatability. So identical, all the peaks are same. This will also measure the droplet velocity. How much, what is the velocity of the droplet? How? If you know the length of the electrode, and if you know the time t1, what is the time at t1 when the droplet is entering the outside from end, And when T3 is a time, when at the bottom end, when the rock is leaving. So at the entry and at the leaving point, if you know the time and also the length is already known to us, you will confirm what is the droplet velocity. So this is basically the response curve because we are noting down the capacity value with respect to time. Finite data acquisition there. Then velocity is given by L by T3 minus T1. So this is what I say. This is the T1 and this is the T3. Velocity is 40 seconds. This is a 70 seconds. So 70 minus 40, 30 seconds and length of the electrode in meter. So this is going to give the velocity meter per second. Okay, this is the deep reading. You see, we do experiment over a period of 30 days. No drift is there. This is a calibration curve. And almost we want to do the fielding. So with fielding, we are having a better capacity value. But without fielding, there is a less capacity value. Interference is more. So that is why fielding is important. This is one more application of the cross capacitor. This is for detecting the metal particle lubricating wire. So what is the metal? Idea is that lubricating wire is basically you can say it is an engine wire. So that is engine wire because of presence of some metal particle during wiring and clearing. It is going to have a malfunction of the rotating path automation. So we need to detect some online detection is required if there is some metal particle of sufficient size is present or not. So this is the same capacitive sensor we have used for metal particle detection. So this is the schematic. This is our machine. This is the lubricating must be while passing through the filter. This is the reservoir with pump. Pump is taking the wire, going to the machine. Then it is filtered. Then it is going back. Okay. So here we have to place the sensor to see whether there is a metal particle in the lubricating wire or not. This is the lubricating wire. Flow is there. So what is the thing? Determination of metal particle debris in lubricating wire. So let us see, this is the structure. Normal operation, metal particles should be 1 to 10 micrometer particles. It will less than 10 micrometer particles. If it is present, then machine will not have any effect of the metal particle. But if the particle size is more than 10 micrometer, it is having malfunction. So here we do an experiment by taking some late metal particle of little bit more, because we are not able to get this type of particle size. So we have taken a little more, and the same capacitive sensor we have used this one. So this is the start. This one I have used for doing experiment. This is made of burnt material, and this is the lubricating wire. Interface cathode 88750 car, and this is the sensor. So this is basically wire channel going through inside the sensor, and then it is collected on the in the beaker. Okay, and this is the filter is used just to hold the metal particles so that we can repeat the experiment again. So we have been 4 metal particles: 6.2 milligram, 17.3 milligram, 27.8 milligram, and 42.2 milligram. Lubricant oil that is Castrol and the MAC, anything. These are the 2 popular brands used in case of a vehicle application. Okay, and we also use another oil that is called contaminated lubricant oil, which is 1 year old. You can say this oil is rejected. So this oil is also having also they break, you can say some dark, so where dark is there. So this is not a good quality. It means we can also, by using the sensor, we can also say whether the quality of the oil is good or not. This is the response. You see that this is the best capacity value in case of a pure oil. Okay, so what happens when the metal particle pass of size 6.2 pass through this one, you are going to have a sudden peak in capacity value. If it is size is increases, capacity peak increases. capacity is increased. It's 42.2 millimeters. So according to the size, capacity value is also changed. This is the same experiment, but now we do experiment in case of an impure wire, contaminated wire. So what is the difference? Only difference that in this case, your base capacity value is smaller, but here it is more. See, here it is 87, isn't it? So there is a 3 to 4 femtofarad capacity change there. Okay, you may tell that it's very small capacitor. Okay, yes, that is only the disadvantage of the cross capacitor. Capacitor value is small, but we can increase the capacitor value by little taking more precaution. That can be done. But still, we are having some interfacing circuit easily available in the market, which it can be easily seen. So see, for either wire, there is a more base capacitor value. That itself it is indicating that it is basically the indicator. In case of fresh one, this value is smaller one. Okay, then it is repeatable for 3 identical. This is for identical peaks. Then one more application that we have explored, that cross capacitive sensor for humidity detection. So here what we have done, that we have tube a quartz tube, hollow tube, and inside the quartz tube we deposited metal oxide sensing film, that is aluminum oxide that we have used for sensing humidity, and we place 4 cross electrodes on the outer surface of the quartz tube. So this is a quartz substrate cross capacitor. Inside there is a 2 dielectric layer. One is glass substrate and another is a moisture sensing film. So it is basically the structure shown here. This is a quartz tube. Inside there is a moisture sensing film, L2O3 film, and outside there is a electrodes is there. So 4 terminals. And this is the schematic setup for conducting experiment for measuring humidity. So this sensor is basically non-planar. In other cases we have discussed the planar type of sensor. So in non-planar, the one advantage is that we can easily place the sensor in the pipeline. Suppose there is a pipeline system there. Gas is flowing through the pipeline, and we have to measure continuously the moisture level or water level there. So we can, that sensor can be part of the pipeline. Because if you place this sensor within a metal case, then its reading should be much more better, and it can continuously measure the moisture level of the gas, or you say any pipe and the fluid that is passing through inside. So this is using again this is another new application that we have explored, that cross capacity sensor for humidity measure, and this is the reading. You see that as the humidity moisture from 0 to 90%, capacitor value is also increasable. So you can see around 50, 45 femtofarad to around 220 to 40 femtofarad. This is the hysteresis error for increasing humidity and decreasing humidity. This is basically a response recovery time. And this is the, so your response recovery time little more. Why? Because you are having a long path. So here path is more, area is also more, sensitivity is also more, but it is going to be a little bit more response time. But suppose you are measuring gas or moisture, and that time is not much crucial. So this is basically the trick to conduct its over a period of 30 days. Okay, and this is the parameter. This is the sensitivity to range 0 to 50 to 96. This is accuracy, resolution. This is the response time, repeatability, drift, and this is the more experiment conducted one with sensing film and with sensing. In the mirror sensing film, we see response is very small. But with sensing film, though it is non-linear, but it is quite significant. So this is one more application of the cross capacitive sensor for humidity measurement. So what is the things is that the cross capacitive sensor has superior response characteristic, non-invasive, low cost of electrode contamination, wide range of various applications. Now, one more application I want to explore, that is the extension of Thomson-Lamport theorem for humidity measurement. So that is the previous for capacitive sensor for droplet detection, lubricant oil quality monitoring, and also the humidity measurement. But now it is another extension of the Thomson-Lamport theorem. This is called cross-conductive sensor, or it is a conductive sensor for humidity measurement. So this is the extension of the Lamport theorem to measure humidity, which is based on resistive technique or conductive technique. So this is the sensor structure that we have fabricated. So this is in fact that we want to measure moisture. Let us see, this is the structure that we have fabricated. So it has 4 cross electrode. But here electrode height is very small. It is a thin film form. Okay, and this is basically a metal case. So this is the structure of the cross-conductive sensor, which is based on extension of Thomson-Lamport theorem. So how the things is there? The capacitance C for a dielectric medium epsilon, let us see epsilon R between 2 electrodes. This is the capacitance expression. You must be knowing if it is EMF, electromagnetic field theory. But capacitance can be given by epsilon surface integral of electric field to line integral of electric field. Okay, between the so this is basically expression of capacitor. Now this is the expression for dielectric medium. But now if the dielectric medium between the electron is replaced by conductive medium, whose conductivity is sigma. So in this case, we are having a 2 electrode separated by dielectric medium or dielectric constant epsilon, and in that case, capacitor value is given by this expression. In case of a conducting medium, conductance is given by Z. This is the same expression. And only here we are having the conductivity value. Now, if you compare equation 1 and 2, we are having C by epsilon is equal to G by, if you take this is here, it is the same, right side is same. You can write C by epsilon is equal to G by sigma. So, this expression can be extended. In case of a PL cross capacitor, this is the expression that I have already told you, given. But in case of a cross conductance for this structure, because this is the cross conductor, this is cross conductance, then the expression becomes epsilon minus. Dr. Bipin, are you telling something? Hello? Am I audible?
Yes, sir, you are audible.
Oh.
Hello?
So, yes. Okay. So, what I am trying to tell you, telling something to me? Okay, what I want to tell to you, that now we are trying to extend the principle of cross capacitor as principle of cross conductance. So in this case, if it is in case of cross capacitor, we are having this expression. So according to this theorem, C by epsilon is equal to G by sigma. So we can write epsilon minus pi G1 by sigma plus epsilon minus pi G2 by sigma is equal to 1. So this is G1, G2 are the cross conductors. So if G1, G2 similarly in case of the cross capacitor, if C1 is equal to C2 or CAC is equal to CBD, then we are having basically C cross capacitor. Similarly, if G1 is equal to G is equal to G0, then we are having a sigma conductivity of the medium is given by pi Z0 L L2. But G0 is basically the conductance value. It is a reciprocal of resistance. And L is the height of the electron. Okay, and Ln is the constant value. So here if L is fixed, then pi Ln2 is fixed. Then conductivity of the medium is directly proportional to G naught. Okay. So if humidity, if this medium is hygroscopic or hydrophilic, the medium conductivity change is according to the humidity. So G naught value will change. So by measuring G naught, we can measure conductivity and also we can measure the humidity. And that is the idea of humidity sensor. So this is the structure. We are having 4 electrodes, and inside there is a dielectric meter which is hydrophilic, and that hydrophilic meter is made of aluminum oxide. That already I have told you. Aluminum oxide I have used for a hydrometer, for parameter capacitor, for cross conductive sensor, now cross capacitive sensor, now cross conductive sensor. So this is basically the dielectric medium, and this is the efficient image of the sensing field. This is the AFL. So this is, as already I have told you, that this is the simple structure element where having 4 electrodes are made by screen printing technique. Okay, and then we deposited this sensing field inside this 4 electrode, and we take the plasma. So you see, this is the fabricated sensor. This is one. This is another one. This is another one, and this is the, it is in case. This is the enclosure. Okay, and this is basically the parameter. Definition. Okay. So what happened when sensing film, this is heated at 420 degrees centigrade temperature, it is showing the surface area of the sensing film inside. Why it is transparent in the outside, it is transparent film is not visible. See, aluminum oxide is a transparent film. So that is why it is not, film is not visible because it is transparent. So this is 220 surface area. This surface size, pore size around 10 point less than 10 nanometer. And this is micropore volume per gram. This is the, at 900 centimeter. This is the surface area. This 900 degrees centigrade temperature. This sensor is enclosed in a package. So it is just like you can say PCB package. So it is a sensor. So if you ground A and B, these are sensing terminal, B and P are grounded. Then you have this GAB actual conductance, and A with respect to D ground with respect to C ground. This is the parasitic conductance. So by using some circuit, this conductance, this current can be nullified. How? This is the circuit. So I have used one circuit. This is basically 1 plus, this is minus VI plus VI. And this is placed at the, this is a summing amplifier circuit. So this is a virtual ground terminal. This is virtual means this is the virtual potential. So this effect will not be there. And this is basically a, you can say, conduct with respect to this input voltage. It is in parallel. So this is also not going to reduce this voltage level. So only this effect will be there at the output. So at the output expression, you can find GAB is equal to GX. This is GX plus V out by V in and GF. This is GF. This is GX. So GX into on the RF, GF is on the RF, and we have seen the drive condition. This is sigma AB and sigma D is different only 0.05%. This is the response humidity, 10 to 90% RS. See conductor value how it is varied with changing humidity. This is the output voltage. This is the transient response or step response. For dynamic, this is basically, this is the static response. This is the dynamic response. Okay, and this is the overall response characteristics. And this is the comparison. See, normally RH is made by detected by interdigited electrode sensor. This is IDT sensor. Now let us see, in case of IDT sensor, the express is very complex. It is empirical. You can say complex, and it is complex electric integral is required. Lots of approximation is there, but this is exact relation. Simple, exact. Complex, not exact. Accuracy depends on film thickness. Simple 4 electrodes, easy with low system, high. Why? There is no sorting problem. Electrode, because there is a lot of gap is there between electrode. And another thing is Roic sensing area is available in master condensation. So these are the feature of the device with respect to size also very small, miniature size. Okay. Now that we begin, how much time is left for me?
Yes, sir. You can take, sir, 5 minutes.
5 minutes.
Okay.
Oh. So last, actually, I want to take one circuit, then I am to finish it. See, this is basically again on more application. That is the structural health monitoring. Okay, and on there is one circuit also there for displaying the prototype system. So I think I should explain that circuit, then I will finish my lecture. Okay, this I will skip. So interfacing circuit for capacitive sensor. What I have discussed in the middle, I have told you the development of digital hygrometer for PK master measurement. So in that case, I have to show the prototype which are reading to you. Okay. So for that we need a circuit. So that is why we develop on circuit. This is based on active displacement and it is based on relaxation oscillator. So you see this part is your relaxation oscillator, this is the integrator, this is having summing integrator, and this is your hysteresis comparator. And this is your active bridge, where we are having this is a capacitive sensor, pure capacitive sensor, and this is info reference one. So this is in fact a active bridge where output of ETT is basically depends on the capacitive value CS, and this depends on the humidity or moisture. So accordingly, due to moisture, this value will change. So this CC will change. Now this is input to this summing integrator, and output of which applied to the relaxation oscillator. So if you simplify this expression, your this is delta, that is delta is given by here, this 4 bridge, 4 arm of the active bridge given by CS by C naught, R2 by R1, R2 by R1. These are the fixed value. So this is, let us say 1, 1, 1 K, 1 K. This one value is there. This is also different value is there. So your output, then you can take the capacitor here also. So in this case, you are having 2 capacitor, 2 resistor. But here what is there? All 4 are capacitor. Then this is also expression. This is one more expression. 2 resistor, 2 capacitor. One more structure. And this is the frequency, this is oscillator. Its frequency output is given by F is equal to F naught, 1 plus K1, CSX minus C naught by C naught, R1 by RS. But RI by RS is basically the, what is RI by RS? This is RI. Okay. And there should be some RI basically. This is the RS, this is RS. So output frequency depends upon, this is factor is constant. This is also constant. So this factor varies. So output frequency increases with increasing capacitance value. Okay. So this is what is said. So this is for humidity sensor. This is for and this is epsilon R. This is how to measure epsilon R. CX epsilon CX. This is interface using microcontroller. So this is your circuit. This is your sensor. This is calibrated sound meter. This is when output is square signal. We have to measure the time period or frequency. So it is at pin number 33. We are having certain program. We will display on the LCD. Okay. So for different master, we are having a different type of capacity value, frequency, calibrate in terms of. So this is the PCB. This is the display on display meter. So it's a frequency which is shown here, maybe some 4.88 hertz. So so 10.488 kilohertz and peaking 100 people. And this is the deep and meter characteristics. Okay, it is in, and this is the calibrated reading. mass check कितना on meter. This is mass reading shown by the viewfinder meter commercial. This is both are calibrated. Okay. So finally, what I want to conclude here. So in this presentation, I am trying to describe different type of capacitive sensor, places for condition monitoring application. All the cross capacity, cross product sensor shows superior characteristic, sensor fabricated at local or legal application cost. And with this, I end my presentation. Thank you, once again to Richarding, NIT, Dr. Deepan, and all these participants for their patience hearing and presenting for this lecture. Thank you very much.
Uh, Thank you, sir. So I want to request all the participants, if you have any query, so then you can please ask, or you can write the chat box in the chat box.
You're welcome. You can ask me. You can also write a question on chat box also.
Yeah. I think, sir, we are just seeing that everyone has writing that your session was very much informative, and
Oh,
we
thank
have
you.
tried a lot of your session.
Thank you very much.
So I think if you have any queries, then you can ask after the session also. You can mail to the sir.
Yes, yes. I have already, I think, in the first slide, I shared my PPT to you. Please, if you have any query, anything, please let me know. And thank you very much for it. This is basically a long session. You must be tired. But one good thing is that nowadays, people are in home, they can drink tea also. Whatever they want, they can tea. And also, they can attend the lectures also. This is a good thing nowadays.
Uh, Thank you, sir. Sir, we are very much grateful to you for spending your very valuable time with us. And you have started the things from very basic, from the capacitive formula, and after that you have just elaborated that how every aspect of this parameter can be changed and it can be utilized for the measurement of moisture, pressure, and also you have seen all the design and fabrication aspect, and you have shown the experimental setup as well as the results. So all of the research scholar who are joining this session, they are I think they have received a significant knowledge about their research topics, and also they can use your just information whatever you have delivered. That was very excellent, sir. So we are very much grateful to you, sir. And in future also we expect that if you possible, then you can please deliver another session. So
Okay.
yeah, with this, just I want to conclude this session. Thanks a lot.
Hello, basically I want to also thank Professor Tariqul Islam Sahab. Very informative lectures he delivered on capacitive sensors, and we have got different options of research, and especially for research scholar and guides also, there are many tips for future research and what are the parameters we have to cover in analysis and designing fabrication. This is an eye opener. I am very grateful to Professor Tariqul Islam, Jamia Millia Islamia, and I want that he should also give more chance to us to get benefited from his lectures.
So thank you, sir. It will be also good thing. I have also, you are always welcome. If you can help or interact, it will be my pleasure. And really, I will feel very happy if you can contribute something. Yes, you are also always welcome, sir. You are always welcome. And thank you very much for giving an opportunity to have interaction in this pandemic period. And I really feel this is also, I think, in future also we have our interest will continue in future also.
Yes, sir. Thank you, sir.
Thank
Thanks a
you.
lot, sir.
Okay, so thanks to all of you once again. Have a nice time. Okay, please
Thank you,
take
sir.
care.
Thank you, sir.
Thank you.
So dear participants, Dear participants, now thanks to all. Now we are entering into next session. So in this session, this talk will be delivered by scientist Sushil Kumar Samwal, who is from DRDO, and the title will be Infrared Technology and Instrumental Perspective. Now I request to Dr. Anup, please organize this session. So over to Anup, please, sir.
Hello, good morning to everyone, and I please welcome Sushil Kumar Semwal sir, who is a scientist in solid state physics laboratory in DRDO, Delhi. He did his BTech in electronics and communication and MTech in instrument technology from IIT Delhi, and his research interests include IR detector. Uh, so, please, Sushil sir.
Good morning to all of you. Am I audible?
Yes, sir.
Okay, so just a second. Hello.
Yes, sir.
Okay. So good morning to all the participants, and I'm thankful to organizers and especially Dr. Anup Sharma and giving me an opportunity to have an interaction with all of you. So today in this lecture, I will talk about infrared technology. So infrared technology is in true sense a multidisciplinary technology with a complex integration of material, mechanical science, mechanical engineering, optics, and device, electronics, VLSI, everything. Everything is integrated into a single thermal camera development. So every complex technology is integrated to form a small thermal emitter. So though it had started from a single detector, but with the evolution of various technology, today it has reached around 4K by 4K array. So I'm sure that you all will agree with me that instrument technology had huge contribution toward it, but it should be understood that mutual support, which leads to it. For example, various technology, example microelectronics, mechanical material, etc., helps in developing better instruments, and in turn, these better instruments help in further developing these technologies, and this cycle goes on. And science and technologies thus grow exponentially, which is being observed by all of us in last few decades. So today my focus of lecture will be on giving a glimpse to all of you that just involving even a single technology demands a huge amount of infrastructure. So let me just start with my presentation. Is my screen visible to all?
Yes, sir.
Okay. So basically, infrared technology is an integration of infrared detector with signal process electronics And since the technology that I am will be talking about today is a cooled IR technology, so it need a cooler to cool down the temperature up to cryogenic temperature. And for this, a cryo cooler is used, which I will be discussing later on this presentation. And the signal to be detected is focused on the detector with the help of infrared optics, and the optics also blocks the visible radiations on the detector. So we are getting only the infrared radiation through the optics on the detector. So all these things are mounted on camera chassis platform, and which is then integrated to form a thermal camera. So in this integrated form, actually we are not able to see where the sensor is. So it is here hidden somewhere. So let us expand this whole integration so that we can see each individual part separately. So here the expanded form of a typical thermal camera, which consists of a infrared lens. So basically it only focuses the infrared radiation of the choice onto the this part is basically our detector, in which the detector is housed. So this is known as Diwar, and for cooling it we have a container which have the liquid nitrogen or helium, depending on the type of application, for cooling this Diwar in which our detector is housed. And finally the electrical signal that is that we obtain from this detector through the electrical pinouts in Diwar with the help of these electronics, which is then further processed, and we get this in the form of electrical signal depending on the typical application. So so what we have, okay. So when we go to the IR technology, the steps are sequentially described here like a detector. So first we have to develop an infrared detector. So in our case, the IR technology that I will be talking about is MCT. So it has to be integrated within ROIC, which we will be discussing later on in this presentation. Here, hybrid refers to the technology where detector material is other than silicon. So to understand it, we have to revisit the history, where initially there were single detector. So processing the signals was easy. Then came a linear array. So here the actual complexity started. As for example, if we consider a linear array of 1000 detectors fabricated linearly, so processing these signals by discrete electronics was quite difficult. So for that, VLSI chips, that is basically readout circuits, had made this task easy. And further, this has complicated when 2D array, that is basically 2D image, or to creating 2D image, 2D array detectors were developed. So for example, consider even a quad VGA format, in which there are 320 cross 256 detectors, and that approximately around amount to around 80,000 detectors. And now it has reached to almost impossible category for discrete electronics to process. So here the VLSI chips required for signal processing and converting it to a usable form for a discrete electronic. So therefore, whenever sensor is not silicon, for example, in other technology, for example, MEMS, the sensor is also fabricated with the help of silicon technology. So there, the detector is monolithic. For example, all process is done in silicon fab. So a single process line can be established for fabricating such sensors. But in this, for example, the case we are taking here, the sensor is basically MCT, and our readout has to be fabricated in silicon only. So a hybrid technology is defined where the detector is of different material and readout IC is basically silicon. So since our detector material is MCT and ROIC is must, so after integrating the detector, it is mounted in a suitable package. Now, MCT is basically a low band gap material. Hence, at room temperature, it will not work. Hence, it needs to be cooled down to cryogenic temperature, which is around 80 Kelvin or around minus 200 degrees centigrade. So for this, it is mounted in a special package known as Diwar. Diwar is basically a double layer container in which the in-between layer is in vacuum. So basically, we have to maintain the sanctity of temperature as well as the electrical signals that we have to process ultimately. So the wire is then interfaced with required electronics for further processing of signal, and this is then integrated with infrared optics in the thermal camera chassis. So final output from the thermal camera depends upon the application. For example, in handheld thermal camera, the final output is basically an image and a screen on which the actual thermal image is being shown. But for example, in missile application, it is basically an digital signal which has to be transmitted to the ground control where the basically missile is being controlled. So before moving on, we will have a brief overview of infrared. So though we will not be discussing the physics, but I suppose it will help in appreciating the actual work that I will going to present in my coming slides. So before this, it is necessary to understand that why even there is an infrared. So as we all know that else of absolute 0 Kelvin temperature, the electrons in atoms are in continuous motion. So higher the temperature, more energetic are electrons. So and thus they radiate accordingly with the wavelength invisible to human eye. So even we know that there is an yeah. So how even because it is not visible to us. So this came into existence after the Sir Frederick William Herschel's experiment in 1800. So he wanted to know about how much heat will pass through different color filters. So he used to observe sunlight and noticed that the filter of different color seemed to pass different amount of heat. So he thought that the colors themselves might be of varying temperature. So he devised an experiment to investigate this thing. So he directed sunlight through a glass prism to create a spectrum and measure the temperature of each color. So he used thermometer with a blackened bulb so that the more amount of heat can be absorbed. So as he measured individual temperatures, he noticed that temperature of colors increased from violet to red part. So after noticing it, he measured the temperature just beyond red where apparently no sunlight was there. So to his surprise, this region had the highest temperature. So he also found that these regions were refracted, absorbing and transmitting similar to other visible light. So since it was beyond the red light and infra means below, this spectrum was defined as infrared, below red region. So it was an important experiment to show that there is a portion of light that we actually cannot see. So only after that the infrared spectrum came into existence. So now we will try to visit some governing laws of radiations. So first of all, sorry, Planck's law. So it was formulated in 1900 by a German physicist, Max Planck, for spectral energy distribution of radiation. So Planck's law of energy, E lambda, radiated per unit volume in the wavelength interval lambda to delta lambda. That is the delta lambda difference. It can be written in terms of Planck constant, speed of light, Boltzmann constant, and absolute temperature. So for temperature up to several hundred degrees, the majority of radiation in the infrared radiation is the infrared radiation. So at higher temperature, the total radiated energy increases and the intensity peak of the emitted spectrum shifts to lower wavelength or shorter wavelength, so that a significant portion is radiated as visible region, as we can see in this diagram also. Like for example, if it is in visible region around 5000 Kelvin, so the peak comes at around 0.5 micrometer. So if we go to lower temperature, for example 3000 Kelvin, so the peak wavelength comes around 1 micrometer. So another is the Stephen's law. So it states that the total radiated heat power emitted from a surface is proportional to the fourth power of its absolute temperature. So it is a very important law for radiations. And now is the Wien's law. So it is also called Wien's displacement law. So it gives the relationship between the temperature and the wavelength at which it emits the most light. So it was his idea to use an oven with a small hole, and any radiation that entered through the small hole was scattered and reflected from the inner oven wall. So when found that the radiated energy that sorry, dW per wavelength interval delta lambda has a maximum at certain wavelength lambda m, and the maximum shifts to shorter wavelength as the temperature T's increase. And he found that the product lambda m, that's the peak wavelength, and the temperature is absolute constant and is equal to 0.2898 micrometer. 2898. If we termed it in form of micrometer and Kelvin. So here given, for example, the temperature and the corresponding wavelength, which can be determined from this relationship also. That is, for sun, it is the temperature is around 6000 Kelvin, and lambda will be around peak lambda will be at around 0.5 micrometer. And the terrestrial objects which are at around 300 Kelvin, the peak wavelength will be around 10 micrometer. So as we understand that every object is not at 0 Kelvin, emit some amount of infrared radiation. Then if there every object is emitting and is emitting every wavelength, then why even there is an infrared band? So it happens due to absorptions by water molecules, carbon dioxide, ozone, etc. in the atmosphere, which attenuate most IR wavelength to some amount and some wavelength drastically, and this leads to window in which the radiations reaches to point of observation. So whatever radiation reaches to point of observation not only depends on IR band but also on the emissivity of the radiating object. So emissivity is basically defined as the ratio of radiant emittance of real body to that of a black body, which are at the same temperature. So it depends on the type of material, its surface finish, wavelength, and the temperature in which the body is. So emissivity of various objects are enlisted here. For example, if a black body emits, ideal black body have the emissivity of 1, so and it goes down to the 0.1 for the glossy metals, so which do not reflect. So another important thing to understand is the contrast. So it is basically the difference in luminance or color that make an object distinguishable. So it is defined by the difference in color and brightness of the object within the same field of view. So our visual system is more sensitive to contrast. So the maximum contrast of an image is the contrast ratio or dynamic range. Mathematically, we can define it as ratio of difference of radiated emittance from the target and background, and with respect to the sum of the radiated power of by the target and the background. So if we see that, it will be the difference of delta P over 2P, and so as we know that P is sigma T to power 4, and if we differentiate it, we get 4 sigma T to delta T. So substituting the value, we get the contrast as twice of delta T and T, where delta is the difference in temperature between the objects. So in real world, the visible scenes have a low pedestal and high contrast, and contrast means the difference in the radiating wavelength between the nearby objects, whereas in IR scenes they have high pedestal and low contrast. So this has serious implications for IR detector. So this pedestal and contrast, let us try to understand it more with the help of these in this slide. So the low pedestal means low actual background, and the signal is basically as prominent as the pedestal, whereas in the infrared the pedestal is very high. That is the for example, in terrestrial scene, the normally every object is at 300 Kelvin. So pedestal is far more than the contrast, because the difference in these objects is very less. So signal with respect to pedestal is very low. So for processing the signal, the background suppression is must in case of infrared detectors. So the advantage of infrared over visible can be explained in present slide. So the scene in a visible region spectrum is heavily dependent on the conditions. Like if it is daytime, it's fine, but it's night, then we are not able to visualize the things, and it is also worse in case of either fog or haze or dusty weather. So, but if we take the infrared image, it is independent of all such conditions. Like in daylight also, in night also, or in a foggy, hazy or dusty condition also, we have almost a similar view of observation. Now, having that bare minimum understanding of the infrared basics, we can now move on the actual focus of the lecture, that is the detector and allied instrument technology, which as can be seen from slide is only a part of complete IR technology. But it is to be understood that it is the most critical technology governing all other things. So today our area of focus of the lecture will be only this part where there is a divar and the cooler. So cooler are basically of two type depending on the application. Sorry. So in the ground application where the thermal imager is need to be used again and again, Stirling cooler is preferable because it work on the Stirling cycle and take electrical power for operation, and hence if we are able to give the power, it can work for long and can be used repeatedly. Whereas in application, for example, in missiles where we have a stringent requirement of load and power, so we can't, and it's only a one-time use. So we are not having the requirement of multiple use and duration of use. So for a typical missile application, the duration is at most 10 to 15 minutes. So this is the maximum amount of time that our divar or basically detector needs to be cooled. So depending on the application, Stirling cooler or JT cooler it utilized. And here is a cross section of a typical divar, which consists of a header on which the detector is placed. So if we consider, try to understand the various parts of this detector, so it has an inner tube which is basically cooled with the help of either Stirling cooler or JT cooler depending on the application, and in between area it is in vacuum. Here is the pinch off tube which is used for creating the vacuum, and after the desired vacuum is achieved, it is pinched off, so to maintain the vacuum inside the chamber. So this basically inner tube is made up of stainless steel, so that the end part which is cooled, so to have minimum thermal loss through this wall to this outer area. So this ultimate this is called cold finger. So on the cold finger the detector is placed and then covered with a we call it as a cold shield, and above it is a field stop which is in which create the required vacuum inside. So one may ask the question that why these two layers are used in front of this detector array. So this is basically because if this cold shield is not used, then since this outer shield is in the is at the temperature of atmosphere, so whatever scene that is being focused from the optics to the detector will have an extra noisy thermal signal generated from this outer cap, because since it is at a temperature, a room temperature, it will itself radiate according to its temperature at which it is. So this cold shield is in direct contact of this cold platform, which cools this inner shield also, and since it is in vacuum, So it will avoid any generation of moisture as that can happen in the outer shield if we try to cool it also. So this cold shield is at the same temperature, that is at cryogenic temperature around 80 Kelvin as per our requirement. So it blocks all the noisy thermal radiation, basically undesired radiation from the outer shield into the detector. So from this, from the optics, we get the desired seen radiation directly on the detector, which is then which is then accessed through these feed through to our electronics. So in later stage, we will have a better cross-sectional and individual one-to-one explanation of these components. First thing first, if we want to detect an infrared signal, so we have to have a choice of detector. So for detecting our infrared radiation, so it also depends on the application. For example, depending upon the nature of target to be observed, the band is selected. So it was discussed in earlier slide that peak wavelength radiated by an object depends on the temperature of objects, and then will decide which material and detector structure will be suitable for our applications. So if we want to have a detector material, what can be the perfect material for our purpose? So it should be a direct band gap material. So that is the excited electrons will directly jump and contribute to the electrical signal generation, and the band gap should be equal to our atmospheric window. For example, if we want to sense an MWIR wavelength, then the band gap of the material should be 0.3 electron volt, and if we want to detect LWIR band wavelength, so it should be around 0.12 electron volt. And above all, since we just do not want to make detector material, but we want to make it efficiently so that the quality and cost of the detector should be as optimized as it can be. So growth capability and process maturity should be somewhat of silicon technology. So this is the, if a material is having these properties, then it will be perfect for our applications. But there is we don't have such a perfect material. So what are the alternatives? So alternatives are basically either we do the alloying, that is mixing of semiconductors with narrow and wide direct band gap. For example, in our case, mercury telluride, that is a semi-metal, and cadmium telluride, which is wide gap semiconductor, is alloyed to form a mercury cadmium telluride based detector. And the advantage is like by changing the composition of mercury, we can tune the band gap so that we can create a detector material with the help of same mercury cadmium telluride for the band of SWIR, MWIR as well as LWIR. The same material with the help of little tweaking in the composition, we can have every band detection. So this property is basically available in MCT only. So that's why till date it is the best IR detector available. So for example, another method is lattice engineering, in which the varying the material lattice on quantum scale. For example, in T2SLS, that is strain layer super lattice based infrared detectors, by varying the lattice layer thickness and the number of repetition of these layers, we can modulate the band gap detection. So for example, I have 1000 angstrom of layer, which is repeated 100 times, I am able to detect MWIR wavelength, band wavelength. And if I change it from 100 to 500, then I can detect LWIR also. So so it has an advantage like MCT, that is without changing the material, just by changing the either composition as in case of MCT, or by the growth method, we can select our desired band gap detection. So but the T2 SLS based detectors still are not at par with MCT, so they are still in the research area. And another method is like by using quantum wells, we can also have multiple waveband selections. So another thing that we need to understand, that detector is also described based on the principle of operation. So based on principle of operation, we have typically two types of detectors. One is a thermal detector and another is a photon detector. So thermal detectors are basically bolometer, pyroelectric or liquid crystal based. So they do not need any cryogenic cooling, are low cost, light, rugged, because then another component of cooling is not there. So as we all understand that reliability increases as the number of component in the system decreases. So because of this also they have a low power consumption, no cooling is required, so instant start is there. There is ease of fabrication, but then down thing is like it have low detectivity and slower response. Whereas in photon detector, since directly the photons are detectors, to have a faster response, higher detectivity, and since higher detectivity, it can be used for detection at longer range. But then down is it needs cryogenic cooling, which increases an extra component. So technology is really difficult, and because of this difficulty, the ultimate cost of detector fabrication is very high. So if we go by structure, so a thermal detector have actually an absorber layer, which is the actual detector or the sensor which senses the infrared radiation and increases the heat over the layer, and which then changes the temperature parameter of the thermometer. For example, if it is a resistance based thermometer, then its resistance will increase. If it is a CBAC based device, then its voltage will change. So basically then absorber increases the temperature which is sensed by thermometer, and as we had discussed that readout integrated circuit is the compulsory component, though, to reduce the leakage of heat from the absorber to the readout circuit, because if heat is leaked, then that necessary heat which could have been used for increasing the temperature will be wasted. So a thermal insulation is used in between thermometer and readout circuit, so the maximum heat could be contained and the temperature can be increased. So whereas in photon detector we have directly a photo detector and a readout circuit, and we get the signal. Though from the structure it seems like photon detectors are very simple and straightforward, but all this simplicity is lost while fabricating the photo detector only. So the photo detector itself is relatively far more complex than absorber, thermometer, and thermal insulation structure that is required in thermal detector based thermal cameras. So when now we have the detector. So we need to compare each of them. For example, how to see that if my fabricated thermal detector or detector is basically infrared detector is better than another one. So the key parameters that defines thermal and infrared detector is responsivity. So responsivity is basically for giving infrared radiation input, how much electrical output is generated. So this depends on the quantum efficiency, the spectral range of operation, fill factor, and spatial uniformity. So basically, these factors will decide that for a given IR input, how much electrical output will be generated from the detector. So noise is basically a clutter which is overshadowing the low level signal. So it depends on the choice of material, the structure, design of the detector. So though inherently some noise will always be there, but it can be reduced with a clever choice of material and structural design of the detector. So and then another parameter is R not a product, which is basically defines the impedance of detector at zero bias. Here we are talking about the photovoltaic detector. So they are basically operated on sorry, at zero bias. So it is defined as an impedance of detector at zero bias and its junction area. So it should be as high as possible so that the maximum amount of generated signal from the detector can be transferred to the readout circuit. And another parameter is uniformity of response. So since our intended application of detector is to create an infrared image, hence pixel array should have a uniformity of response to create true image. So with uniformity of response, it is required that all pixels should perform. So it is defined as the pixel operability, and the detector array is categorized based on the percentage of operational pixel and presence of non-operational pixel in cluster form. So to have a good contrast in the image, there should be no spatial crosstalk between the detectors. So else intermixing of signals neighboring pixels will reduce the image crosstalk. So, and at the end, since we are talking about the 2D array, in which the smallest format, that is quad VGA, itself is around 80,000 detectors that are to be read. So this detector which we had formed has to be integrated with ROIC, and how well it can be integrated depends on the how ease of coupling is between ROIC and the sensor. Else every work that we had done, or every effort that we done in fabricating that detector is wasted. So now as we go deeper into the technology, where the instrumental requirements then will be introduced. So the detector is fabricated by a process sequence as given here. That is, first of all, a substrate is required on which the actual detector material is grown. So with the help of growing technique, applier growth, there are several methods. So there is requirement of compatibility between that substrate and the applier material. So these two things, the substrate on which the applier is grown has to be compatible, and then we have to do the photolithography process to create the actual detectors on this applier. And finally, since we have to integrate it or couple it with the ROIC, So a metallization process, which is also termed as indium bump growth, is done, which is done both on detector and ROIC. So first of all, we will discuss about the substrate. So substrate in our case is cadmium zinc telluride. So it is the best material in form of compatibility with the MCT epi layer. So as we can see that the two elements, cadmium and telluride, is similar to the two elements in mercury cadmium telluride. So the cadmium telluride itself can be used as the substrate, but with the introduction of around 4% of zinc, its matching is enhanced a lot. So widely only this CZT based substrate is used. So CZT substrate is again have some process sequences, after which only we get this substrate. So first is the crystal growth, and then slicing of the ingots that is grown in the process, and finally before an epi layer growth process, polishing steps is there. So this is the typical list of instruments that will be requiring for this simple substrate, which is at the, I think I don't know if it is appropriate to call, but at the lowermost point of the IR technology, because from the substrate we do the epi layer, then we do the process, then we do integration, then package it, then collate, then integrate in the camera. So I think that it can be termed as the first at the bottommost step of the infrared technology. So this is the list of instrument infrastructural requirement, and I'm not using the clean room requirement, that is the basically infrastructural requirement for this instruments housing. So first step of substrate preparation is the carbon coating of ampules. Ampule is the quartz ampule is basically where the seed crystal is grown, and to have the it was observed and it is also published that when we use the carbon coating on the ampule, though the what I call that distortions or dislocations etc in the crystal are reduced. So first of all, the quartz ampule is carbon coated, and then after charge in vacuum, a rocking furnace is used for uniformity in the grown seed, which is then an ampule is grown on the furnace. Here is the infrastructure requirement. These are the control panels where the different zones of furnace at required temperatures are maintained with the help of this control panel, and around in a week's time we get this CZT ingot. So this is a cutting machine which then cut the ingot in our desired orientation. So this is an CZT substrate that we had got after around, I will say, 10 to 12 days of fabrication process. So that CZT layer is cut into desired, for example, this is our substrate size that we require, and in the actual growth process we get a very large size of substrate. So it is then cut with the help of this wire saw machine into our required size, and then if for example if we require around 800 micron of layer thickness, so that is done with the help of this lapping machine, which removes the excess thickness from the substrate, and then polishing. The same machine is used for lapping as well as polishing, but the attachment are changed depending on our application. For example, if we are doing lapping, then another attachment will be used, and while for polishing, another attachment will be used. Polishing is basically final step where the thickness variation, TTV, which is basically total thickness variation from end to end, is maintained. So finally, after this step, we have our substrate on which the apple layer will be grown. So at SSPL, we are growing this apple layer by the method which is known as VDLP, basically vertical dip liquid phase epitaxy. So the system consists of a furnace in which the temperature is along the height of the furnace is controlled within plus minus 1 degree, and this motors basically controls the dip of the CZT substrate, and after around 3 to 4 days of process, we get this apple layer grown over the CZT substrate. This apple layer is basically around 18 to 20 micron thick, which is then polished to the thickness based on our requirement. So when we have this apple layer grown, so since vapor pressure of mercury is very less, so if we do not passivate the apple layer, so the mercury try to move out from the surface. So the first step after the apple layer and the immediate step after the apple layer growth is the passivation, which is done on this thermal deposition system, in which the this passivation, this is basically a cadmium telluride layer, so which is grown in this thermal deposition system. So after the passivation is done, the actual junction is formed with the help of ion implanter. So this is basically an old ion implanter at SSPL which generate 400 kilo electron volt of ions, and then which are used to create the junction in the apple layer. So this is typical schematic, which is basically on CZT substrate. It is not to the scale. CZT substrate on which apple layer is grown, which is then passivated, and after this on this passivation, this junction layer is created with the help of ion implantation. So basically then we comes to now we are ready with our device with a junction. So we need to basically isolation of diodes, since ours is not a linear structure, we have mesa structure. So the mesa is created to separate out the detectors from one another. So these are the typical instruments that are used for this device photolithography process. So first is this is spin coater for creating for coating the photoresist on the substrate. Then this is a hot plate which is used for baking the photoresist, and then it is this is a mask aligner which is used for exposing a pattern on the detector on that apple layer, which is then developed. And in the developing process, sometime there the traces of photoresist still remains. So for removing those traces, process of plasma assure is done, which basically burn out the leftover photoresist with the help of oxygen ions in inside. So a structure is then a detector array structure is formed over our apple layer. So this after this indium bumping process, basically metallization is done, which goes through the PLG steps as shown here. First we give the first layer, and then we do the flood exposure, second layer, and then pattern exposure. So develop and we get the inverse profile. So basically inverse profile is required because we are doing this for lift. We are doing the metallization, that is indium pumping, by the lift off process. So in the lift off process, the metallization is done blanket, in which due to the inverse profile there is a break in the metal due to this inverse profile. So whenever after metallization we introduce this sample to the photoresist stripper, which is basically nothing but the acetone go inside through these breakage and strip off the photoresist on, and this layer of indium which is over the photoresist is lift off. That's why this process is also called as a lift off, and then we are left with the indium bumps on our required space. So this is a SAM image of indium bumps grown on a test sample. So now when we are done with growing, so it is to be noted that these process steps are similar for both. This step is done on the ROIC also, so the process is same, a little similar. I will not say same. It is similar for detector array and as well as for readout circuits. So after these indium bumps are grown on both the both detector array and ROIC, they are joined with the help of this machine, flip chip bonder, and this is machine which can flip chip integrate. So flip chip, why this is called as flip chip? Because we want to join these two bumps on the detectors and the ROIC, which can be done only by flipping one over the other. So this machine flips the chip and ROIC to integrate. So that's why it is also known as flip chip integration. So it is but I will say it's really a very expensive instruments, and in crores, its cost is in several crores. So this can integrate very large arrays with the accuracy of within accuracy of 1 micron. So it is really a very difficult task to do. So that what I was telling before, that instrument and technology both work hands on hands to develop each other. So this system is used for this image shows an detector array flip chipped on ROIC. So basically this what input required for this process is the force with which we want to press these two chips, that is ROIC and detector, to join, and at what temperature. So there depending on our material, for example in MCT we cannot take the temperature below 60-70 degrees, so we cannot give the higher temperature, but we can take the force up to here the force is around 2 kg, but we can go depending on the size of array up to the 20 kg also. So it basically calculated as the force applied per detector. For example, if there are 1 lakh detectors, so this 2 kg will be distributed uniformly in between those 1 lakh detectors, and then 2 kg divided by 1 lakh will be the force that will be applied on each individual detector. So this is a very critical parameter, because applying extra force can damage ROIC as well as the detector. So this flip chip integration process is to be optimized, and very crucial as well as critical, because after going through several process steps, we had reached to this step. So failure at this step will waste all the effort which are done before, from growing the crystal at the for substrate. So since we are using these detectors and ROIC integration at cryogenic temperature, and as we know that these two different materials are having a different thermal expansion and contraction coefficient, so mismatch of these thermal expansion coefficient can pull apart these indium bombs during thermal cycling. For example, in the testing, we used to cool it and several times for testing. So if I even cool it 10 times, 20 times, it should not take apart these indium bombs. So it's really possible, because indium is by nature is a very soft metal, and that's why it is used in this process, because by simply applying a force, it just mixed together and form a very good resistive contact. So as we see this in this image, this is detector array, and to test the thermal expansion and contraction for our required process, a daisy chain structure is formed, in which so it has been moved somehow, but it will be here on the ROIC part. So a daisy chain structure is created, and we check the resistance at the two end, and if anything happens, so that daisy chain will break, and we will know that our indium bonds have been broken. So the another preventive method that is used in this process is using of epoxy, which is basically cryocompatible. Means this epoxy sustains its property even at cryo temperature, that's around minus 200 degrees centigrade. So this epoxy is filled in between ROIC and detector, which helps in bonding the ROIC detector array and the indium bombs. So it increases the reliability of this whole integration. So finally, then we come to the mounting of this ROIC and detector integration on the header, which is placed on the cold plate of the diwar, as we had seen earlier. So here it's the actual enlarged image. There it was not visible. So this is a detector which have the electrical pattern for having electrical access from outside. So this is ROIC and detector integration is mounted on this header, and then wire bond is done. So this wire bonding machine is used for bonding the wire. So that is basically to have the electrical access to the ROIC, so that we can have these detected signal, which were converted into electrical signal by detector and then processed by ROIC for our discrete electronics. So finally, we have this assembled diwar. So this diwar is basically having a inner tube on which this carrier is placed. This image shows the inner tube with the outer casing. Okay, and on this this diwar is mounted. So from in this we have either Stirling cooler or JT cooler, which cools this area, and then we have this hinge on flange on which is placed here, on which we have HTCC feed through, which is help in taking the electrical connection and then on this sky blue ring we place this cold sheet. So as I discussed below, this cold sheet is through this header. Header is a very basically aluminum nitride material and have good thermal conductivity. So it also cools this cold sheet, and this cold sheet, over this cold sheet is window housing, which is placed over this HTCC feed through, and at this place the silicon window is placed. This copper evacuation tube is basically this tube which is used for creating the vacuum, and which ultimately is then pinched off. So here we have final assembled diwar, which is then before pinch off is checked for leak detection on this leak detection system. So it take the that diwar up to the 10 to the power minus 12 order of vacuum, and then check for if there is any leakage in any joint while fabrication of diwar. So which is then placed in a degassing system for around 15 days. So this system is placed, this diwar is placed in a degassing system for around 15 days with at the temperature of around 60 degrees centigrade. And after 15 days, that copper evacuation tube, that which it is now here pinched off. So this is pinched off with the help of this pinch off tools. So basically air pressure is used to pinch off the copper tube so that a perfect vacuum is managed in the system. So as we had seen the process on the ROIC, but actually before using the ROC it is tested. So we do not want to use our precious detector to be integrated on a non-functional ROIC. So every ROIC that is being integrated with the detector array has to be first tested. So here is a probe station which is used for testing the ROIC functionality, a typical wafer. So we currently at SSPL have a probe station which can handle the wafer up to 8-inch. So and depending on the ROIC design, we have a probe card which is held for electrical connection with the help of probes which are matched with the ROIC pad location. So in this way we do the electrical testing of ROIC. And this is the final test and measurement setup, which is basically optical test bench in which there is a data pattern generator, low noise supplies, ADC converters, frame grabbers, and radiometric equipment, for example, extended area and cavity black body, and monochromators, the optical rail on which the monochromator or the black body is being moved. So black body controllers, etc., are in this electrical chassis. So this diwar is tested with the help of JT cooler in our case, because at SSPL we are using JT cooled technology for diwar, and then the nitrogen supplies is obtained with the help of a bottle which have compressed nitrogen, which is at around 300 bar. So this JT cooler cools the cools our detector, and in this diwar with the help of this flex cable which is connected to our these electrical connections through HTCC feed through, and these electrical signals are generated through this electrical cabinet, and then the infrared radiation basically are used for sourcing the infrared radiation. Black bodies are used. So there are multiple parameters. So depending on the parameter, for example, I want to use non-uniformity. Then I use the extended area black body, which illuminate a complete area, and then we observe the uniformity in the output of detectors. And if we want to observe the crosstalk, so if in crosstalk we only illuminate one single pixel, and with the help of a Cassegrain optics, which can create a point of radiation of around 1 micron, so we can illuminate one detector. And then crosstalk means if we are illuminating one detector, what amount of signal is being leaked to the neighboring pixels also. So several such parameters are used with the help of this IRFPA test and measurement setup. So I think I had was able to introduce the infrastructural as well as the instrumental requirement of the a small segment of complete IR technology, though I had discussed only one, but there are several other methods and materials, structures, and applier growth, etc. for infrared detector fabrication. So I thanks all for your time. So I am free for any questions.
Thank you, sir. Thank you so much for sharing your great knowledge with us, and we are very grateful for sharing to you for sharing your valuable time with us. And thank you so much for a great lecture you have given here about infrared technology, about photodetector fabrication, about materials used for fabrication of infrared photodetector, and about charge preparation and crystal growth techniques. Your lecture had a significant impact on every participant, and some participants have some doubt, and I have pasted in chat box. You can read from there, and if any participant have their doubts, they can write in Google Meet chat box or on YouTube channel, and Sushil sir can give answer to your all doubts. Hello, Sushil sir.
Haji, is anybody asking some question? Anyone?
Some participants have some doubts. I have posted in chat box. You can see.
That need to be texted on, so I will text them.
Okay. So, like that, they have answered. They asked that what technique is used for re-evacuating a metal rebar.
Re-evacuating means I didn't get the question. Can the person reframe the question?
Okay.
So, Ebar, can you please rewrite your question, what you want to say? Actually, sir has not understand your question. And his another question is, what is the use of KBR in an IR detector? I think krypton bromium in an
Potassium.
potassium.
Sir, he has asked some other colleagues question that what is the use of KBR in an IR detector? Okay.
So are you able to see?
Yes, sir. You can tell also, sir. All this your answer now.
So we are basically using bromine iodide for etching of the applier.
Okay. So the next question from the same guy is MWIR compatible to sense heat and flame?
So when we are saying IR, then is basically sensing the heat only. So but MWIR, if we say, then MWIR is basically the temperature of the flame. So if you have to just define what kind of flame or the source of flame, then I can definitely tell that it will sense it or not. So basically, whenever we are saying some temperature, so as I had shown in my slides, that every temperature is radiating every wavelength, but the peak wavelength is different. So as we go on different temperatures, so different wavelength, different peak wavelength is generated. So MWR basically comes in around 3 to 5 micrometer of wavelength.
Okay. So the next question from the same A bar is how is FTIR different from IR?
FTIR is a characterization technique, and IR is basically as William Herschel has defined beyond red radiation.
Okay. So, sir, there is one question more. What is a goniometer? What are the parts of it? And sir, if possible, please discuss about goniometrical
So here we use goniometer only for because we want to generate our crystal in some particular angle from the crystal. So that system basically maintain the angle of growth. So goniometer is basically the angle measurement instrument which is used for measuring the angle. So it also depends upon the type of application. So here it is basically done in the time of crystal growths. Basically, from the seed crystal, we have to maintain particular angle to have a perfect ingot in our orientation. So goniometer is basically for that particular application in our case.
Okay, sir. Sir, one participant named Satish Kumar asked that what are the instruments used for lithography?
That I had already showed in my slides. Like if we do want to do lithography, then we have some spin coater unit, then we have oven or hot plates for baking the photoresist, and then we have to have mask on, and then use a mask aligner which is used for exposing the pattern on our photoresist, and then we have to develop it. So we should have a wet bench on which we do that developing, and then we are done with our lithography or either metallization or etching process. Whatever be the application is done on the developed sample.
Okay, sir. Sir, the next question asked by Pranav that can we detect the presence of explosives material in the air by making use of IR rays?
As I have already told before, that IR means any heat generated from any source. So whatever be the source, either it is an explosive material or a jet plane or a hot paratha, whatever it be. So if there is a heat, then it will generate some IR, and depending on the temperature, we have a IR band, and depending on that IR band, we have to have a detector which is suitable for that particular band.
And sir, last question from Subhajit that can IR detector detect color?
So color, if you are talking about visible region, then definitely not. Color is basically defines the wavelength that we are seeing. So if we are saying about IR, so IR is actually not visible to human eyes. So if you want to say color by if you are referring color to a visible region, then we cannot.
Any other questions from any participant who want to ask any question or doubt from Sushil sir?
RGB color.
Or you can ask in future also by contacting Sushil Kumar Senwal sir on his email. Okay, thank you sir for your valuable time. And sir, one question asked by Utpal is that how RGB color space detected?
I had not got the question.
Okay, Utpal, can you elaborate what you want to ask to Sushil sir? Utpal, are you there? Can you repeat your question? Sir, last question. Why yellow light is used for photolithography?
It is not basically it does not means yellow. It's basically because it has the least amount of UV content, because the photoresist that we are using, that polymeric chain in photoresist are most sensitive to the UV wavelength. So as we go near to that wavelength, the photoresist may degrade. So that's why we keep our lighting system to the yellow region.
Okay. Thank you so much, sir, for sharing your great knowledge with us. And in future also, we want you to give again presentation on your this great knowledge. So thank you so much, sir.
Thanks for inviting me, and thanks to all organizers and especially Dr. Anup. Thank you.
Thank you, sir. Thank you so much.
So for the participants, we have another session from 2:30 to 4, and in that session, Dr. Janardhan Kundu, one of the INA scientist receiver, he has also received an award from Young Innovation Scientist. So he will give the analysis, design, fabrication, and control of attraction type electromagnetic levitation prototype. So we will meet on 2:30 p.m. sharply. So please be on time. Thanks a lot. So for all the sessions, we have already mentioned that the attendance we are providing before the 10 minutes of the end of lecture, and also we are taking the attendance from this Google Meet add-on attendance. Okay, and the link will be common. Google Meet link is common for all days. Okay. Thank you. Thanks a lot.